Welcome back to this series on AI HPC infrastructure. So we're going to continue on containerization. So in the previous video, we talked about how one type of virtualization basically makes use of virtual machine architecture, and virtual machines are heavier weight containers where they actually completely isolate the resources using a virtual machine, which is a software version of a PC or server running within a physical infrastructure by making use of a hypervisor. Now for this part, we are going to talk about a more lightweight version of this, because in the virtual machine, the images have to be very large, since they actually not only contain the application code, but also contain the guest OS code as well. So within the image, it has both the application as well as the operating system that is required to power that particular virtual machine. So when it comes to containers, instead of a virtual machine, we have what we call a container, which is a lightweight virtual machine in some sense. Notice that actually for containers, we do not it does not contain the operating system image. So what the hypervisor equivalent, which is the container engine, provides is just the environment to run the application, and each of these containers or environments are isolated from another container. But the operating system code is not replicated in each container. So that part is actually shared, and therefore the level of isolation is not as much as we would actually get in a virtual machine. So containers are virtual entities that focus on just decoupling the applications, also known as microservices. As depicted in the figure, a container contains all the necessary libraries as well as whatever's inside the file system in order to be able to run the application itself. And we are going to assume that this container is actually running on a common operating system. So we have multiple virtualized copies of this common operating system, for example, Linux, which is basically what the container engine provides to each of the containers. A container shares the same kernel or operating system kernel as the other containers from the host system. So it's actually the host system is going to be a Linux operating system as well, and that kernel from the host operating system is shared across all the different containers. So this is more lightweight, since we're not going to replicate the operating system code. We're just going to have the application and library code itself. One of the common container engines is known as Docker. It's a very common and a well-known containerization platform that enables the adoption of this technology, this lightweight virtual machine like structure called a container. But there are other container platforms besides just Docker. So one that's very common in the high performance computing environment is something called Singularity. So Singularity is a container platform. It allows you to create containers that package up software in a way that is portable and reproducible. And you can build a container using Singularity on your laptop and then run on some of the largest HPC clusters in the world. So this is a more container that's more suited for HPC clusters. And yeah, so for example, in a university or a company cluster, or even the cloud. Another container structure is what we call the NVIDIA Container Runtime. The NVIDIA Container Runtime is actually GPU aware, so it does contain libraries to actually share the GPU resources, unlike those full container applications that we talked about earlier, because it's coming from the GPU hardware company NVIDIA. So the software environment is actually aware of how to share this GPU container, and it's actually compatible with the Open Containers Initiative using Docker, CRIO, and other popular container technologies. It simplifies the building and the containerization of GPU accelerated applications to the desktop, cloud, or data centers. Another container structure is what we call the container platform is the LXC, or Linux containers. This is the operating system level virtualization tool for running multiple isolated Linux systems or containers within the container host. which contains a single Linux kernel. So LXC supports unprivileged containers require in certain deployments such as high performance computing environments. So LXCC3 and later is actually available on various Linux distributions and includes supports for GPU using the NVIDIA Container Runtime. This is the same one here. And lastly, CRIO. CRIO is actually a lightweight container runtime that was designed to take advantage of the Kubernetes container runtime interface, or CRI. So this particular version of the container is particularly optimized for Kubernetes. But Kubernetes is actually quite a common additional tool that's actually used with the containers. It's like a control mechanism for the containers. So what are some of the advantages that containers have over maybe virtual machines? So one thing is that container technologies contain the following advantages. So first of all, it's going to be able to start a lot faster because the image itself is much smaller. So we're talking about seconds as compared with virtual machines, which can take minutes to actually start up. Secondly is efficiency. It requires fewer resources, so it's more lightweight. So you can actually run more containers on the same physical server, as compared with running multiple virtual machines. That's because the container platform is a lot more lightweight in terms of resources that it uses for CPU, RAM, etc. Thus, more applications or more containers can be actually supported over the same physical infrastructure. Thirdly, licensing. Common technologies and libraries used for containers as Docker and Kubernetes are actually open source and they are actually free to use. Therefore, there's no proprietary license for these technologies. Fourth, reuse. A container is basically based on the image, and because it's very lightweight, the image only contains the binaries for the application and the libraries itself, and the container does not, the image does not actually contain the operating system code. So Docker images can be easily built using the equivalent of Vagrant files here called Docker files, which are actually configuration files. And once you have the Docker file built for a particular container, you can easily replicate or spin up multiple versions of these containers as much as you need, right? As long as you have the Docker file available, you can then create instances of these images and run it on the multiple copies of these containers. So, for example, if you have a web server that's configured with all the applications and payment gateways support that you need, and you need now, instead of one copy of the web service, you need web application, you need multiple copies. You can just spin up multiple copies using the same Docker file. Now, the images are typically stored in a more organized structure called a container registry. And these are actually repositories that contain these container images. We'll talk a little bit more about this in the next few slides. But before going into these container registries, let's talk about some disadvantages that containers actually have. So it goes with the lightweight nature. So the level of isolation is not as much as what we will get in the virtual machines. So in that sense, actually the security will not be as tight. So it's possible that there's some leakage of information through the operating system, and the container information could actually be derived right from the container itself if you somehow manage to crack into the underlying operating system. Okay, so because each virtual environment is not fully isolated as we have in the virtual machine case. And containers are also dependent on the OS. So we cannot have multiple containers, each running their own operating system. So the containers are merely running instances of the host operating system and share the operating system service calls across all the different containers. So this actually makes it less portable because we don't have a full independence in terms of how we can actually derive different operating systems in each of these virtual instances. So how is the Docker file actually used to build the image? So there's often a confusion between the role of the Docker file that's used with the Docker build command. And the Docker build command basically builds up the image that can be used to spin up a particular Docker container. Now, and the Docker compose YAML file. So there's another Docker file called the Docker compose file, rather different from the Docker file that we use for the build commands. So Docker file is a simple text file. It just contains commands that are used to assemble the various binaries and applications that's used to actually assemble the image. And the Docker files, in essence, are used to build the images. The Docker Compose is slightly different. Okay, it's a tool for defining and running multiple Docker containers. So if you have an application that requires several containers, the Docker Compose is the way for you to orchestrate or make these different containers work together. So Docker Compose uses the Docker file to build the individual instances, and your Docker workflow should build a suitable Docker file for each of the image you want to create, and then use Docker Compose to assemble those images using the build command. So Docker Compose is mainly used to deploy images or group of images into containers instead of just building the image itself. Just as in using Vagrant, we can automate the creation of virtual machines. We can use something called Kubernetes, short form K8s, as a platform for managing all these containerized applications. It actually provides the following capabilities: automatic container packing. So Kubernetes has a set of nodes. On a set of nodes, these various containers can run with the kind of memory requirement automatically and make use of the best resources for it. Kubernetes can automatically restart if a container goes down and then brings it up again, so it's robust to failures. In terms of the usage of storage, if there are multiple storage system files and file systems, Kubernetes can enable the organization of these file systems and how you actually use it to each of the containerized tasks. You can control rollbacks. If you would need to go back to a previous version, Kubernetes can enable that rollback to a previous version automatically, and it also allows you to discover new containers, right, using a name service. And it will also provide load balancing. So if you have multiple copies and you want to run your application such that each copy will have a certain load, the Kubernetes will do this load balancing for you. And lastly, it also manages configuration management like passwords, SSH keys, etc. This is more for a network of containers with different applications, so you need to manage all this additional administrative stuff that you need to have all these different containers working together. And you can do this without having to actually rebuild the image. So this is what we talked about earlier, where we have the repository. So the container registry can contain a number of repositories, and each of these repositories will contain a number of container images. So in a Kubernetes cluster, which is basically a cluster of containers, we can have different machine learning applications. So machine learning application 1 and 2 here, they actually built up using, they are actually copies or replicas of the same container. So they are going to be picking up the same container image from repository X. Whereas for the orange Kubernetes cluster, they're actually using a different image from repository Y. And we can also have a pipeline for training. So the pipeline for training, typically the image code will be different from the application code, which is mainly for inferencing or running, making the predictions itself. So you notice that for this Kubernetes cluster, the pipeline and also the application for making predictions is running off the same repository Z. And in repository Z, we actually have two separate images. All this, which image is contained in which container, is all managed by the container registry. So ML applications and machine learning applications, we have basically two types. One are basically the applications that make inferencing or predictions using the model and new data. And the second one is the training pipeline, right? The machine learning pipeline that's used for training and also testing, evaluating the machine learning workflow. This is used to build a model. Okay? So the pipeline is used to build the model. The app is basically what uses the model to make predictions. So we can have containers for both training and testing, which is the machine learning pipeline. So you can see that for this cluster, the pipeline code is actually built using this particular image that's shown by the arrow there. So the tasks in the pipeline are orchestrated within the container. So the container could be based on an image that has all the relevant libraries such as the Python, PySpark, scikit-learn, and pandas. And the machine learning code containing library, all the libraries and user code to perform feature engineering, feature model training, everything that you need to build a model, right? Feature engineering, model training, hyperparameter tuning would be contained within this image. So when we spin up this, we are able to just feed it the data, and it will be able to build the image for the application and the model for the application. Now for the machine learning apps itself, you can see that there's two here and also one more here that is actually being spin up from the image. Okay, so unlike the machine learning pipeline, the apps are mainly for prediction, so it only contains the binaries and libraries needed for the application code and prediction itself. So we don't need the additional ones for building hyperparameter tuning. Those would be inside the pipeline's image rather than in the machine learning app. So the machine learning model can be stored in the file system or accessed through the model serving system. So it could be contained within the image for the container, or it could be in a separate model serving system and be pulled down the image from the model into the container itself. Okay, there's two ways to actually do that. The machine learning model image is the image for the application. So it is actually possible that the libraries and binaries used for the images, this is the most common, therefore they are both based on a common custom-made base image, and the model image is based on the code image. It's quite common for modern organizations that adopt a more and more machine learning applications such as those above to use ML platforms from public and service cloud providers such as Amazon, from Azure, Microsoft Machine Learning Studio, as well as the Google Vertex API. All these public cloud providers, they typically heavily use Kubernetes and also containers to deploy these machine learning applications. Now, this just a second point is that it is possible because these libraries, once you have actually the commonly used libraries and binaries within the image, we can then use this to build additional custom images, because the basic components are already configured and made available for the base image. So adding additional software to it, we can then easily customize our image for our own custom application of the base image. So this is actually the other advantage of containers in the sense that they allow you to have a layered approach where you build the base image, and then over the base image you can add on your additional custom code that is specific to your application itself. And then you can reuse that base image that was actually done in a more generic manner. So imagine a Kubernetes service where the applications are basically deployed in clusters of containers, in this case virtual machines in the form of containers, and public cloud companies such as the Azure Kubernetes service, Amazon, these are basically container services, right? Amazon Elastic Kubernetes service and Google Kubernetes Engine. This require very or little management overhead, and such service will use some sort of container registry such as the Azure Container Registry, Amazon Elastic Container Registry, and Google Container Registry, which contains like the domain name lookup, right? You can look up a particular name, and you can locate where that image is found within the container registry. And this creation and archiving of images is supported CI/CD, okay, continuous integration and deployment pipelines such as Azure pipeline, Amazon pipeline, and also the Google Cloud Build. So you can see that for the major cloud providers such as Amazon, Google, as well as Microsoft, they actually have quite good support for this containerized deployment of machine learning applications. Okay, so here's a quick quiz for you before moving on to the other parts of the videos. So containers have the following advantages over traditional virtual machines. So there are a number of answers here. There may be, so the first one is A, containers provide a higher level of isolation. B, containers can contain different operating systems. C, containers are more lightweight and hence more containers can be supported on the same physical server. D, all of the above are true, or E, none of the above are true. So pick one answer and hopefully you are able to do that within the next few minutes. So just pause here while you think about this question and try to think of the answer. Here is another mini quiz question for you. The container repository contains what? Right, so A, it contains Docker files that are used to build container images. B, binary files containing images of the containers. C, the registry of containers. And D, the registry of repositories. So again, just think about this a little while and try to find the answer before going on to the next video. Let's pause it a while. And we come to the last slide. So thank you for your attention and I'll see you in the next set of slides.